Alright, so now what I'm going to do is try to explain number 63. So if you read question 63, it says a sample of a certain monoprotic weak acid. Okay, so your generic weak acid. Was dissolved in water and titrated with 0.125 molar sodium hydroxide, okay, requiring 16 mils to reach the equivalence point, or to titrate it. During the titration, the pH after adding 2.0 mils was 6.912. We want to calculate the Ka for the acid. Okay, so that's ultimately what we're looking for. All right, so first of all, let's back up just a little bit. All right, if we know it took 0.125 molar sodium hydroxide, and there were 16 mils, we can, till the equivalence point. If we come down here and I do my molarity conversion, I take 16 mils, multiply it by 0.125, I figured out that it took 2.00 moles of hydroxide to neutralize. So that means that there had to be 2.00 millimoles of the weak acid originally in the solution. Okay, so that's just you working backwards with the titration math in order to figure that out. Now, for the next step is it says after 2 milliliters, okay, the pH was 6.912. So now I can use that to my advantage in order to figure out the Ka. So if I had 2 mils added and I use my molarity conversion, it means that 0.250 millimoles of hydroxide had been added into that solution. So if I come down to my stoichiometry ice table, so to speak, spell that correctly here, I start with the initial concentration of 2.00 for my weak acid. That's because I know that that's what it took to neutralize it. Now, after adding 2.00 milliliters, 0.250 hydroxide reacted, and 0.250 of the anion was produced, which means that I had a concentration of 1.75 for my weak acid. So I wrote this wrong up here. This should be 0. We're adding 0.25. So what we're going to end up with is 0.25 of the anion as well. Now, to find the Ka, we can do this one of two ways. We can either use the Ka expression and solve for it, or you can use Henderson-Hasselbalch, because here is your base and here is your acid. Okay, now if you want to use Henderson-Hasselbalch, go ahead and try it and make sure that you get the right answer. I'm going to go ahead and use the Ka expression. Now, okay, my Ka expression for any acid always looks like this. You have the hydrogen ion plus our generic, or our anion, okay, and we're going to end up with, the weak acid on the bottom. Okay, so I can solve for it this way. Now you may be going, well, there's no hydroxide. How the heck do I know what the hydroxide concentration is? Well, here, if I think about the at that point, it told me the pH value. Okay, the pH value at that point was 6.912. So what I can do is, using the backwards of my pH equation, I can take 10 to the negative 6.912, reverse of my log equation, and figure out that my concentration of hydrogen ion was 1.22 times 10 to the negative 7th molarity. Okay, so now I have hydrogen ion concentration, I have my anion concentration, and my acid concentration. So I can go ahead and solve for all this. So my Ka, well, sort of, but let me show you what that means. I got my 1.22 times 10 to the negative 7th for my hydrogen ion. Now, for the anion concentration, here it was 0.25. Well, one thing they haven't told us was volumes. Okay, so I've got 2.25, actually 0.250 if I want to keep my significant figures here, over whatever the new total volume was. Now I'm going to show you why it's not important that we had to know that here in just a second. And what I do is I put it over the concentration of the weak acid, which would be 1.75 again over the new total volume. So it doesn't matter that I don't know it, because guess what? I can cancel those out. Okay, so now I just got to plug and chug up here. Got to take 1.22 times 10 to the negative 7th, multiply it by 0.250, divide by 1.75, and get a Ka value of 1.74 times 10 to the negative 8th. Okay, now as a reminder, you could have alternatively used Henderson-Hasselbalch and I know when we originally did Henderson-Hasselbalch, we had the concentrations of the base over the concentrations of the acid, and we addressed this the other day in class, but since the new total volume is exactly the same, if we just know the amount of millimoles, then we can also set it up using Henderson-Hasselbalch. So you could have had 0.25 as your millimoles of base, 1.75 as your millimoles of acid, and you could have gotten Ka that way as well. Okay, either one would have been a viable possibility. Okay, so that is 63. Now let's go ahead and talk about 65 and 72, and then I'll probably make a last one, another video for the last ones that deal with KSP. All right, so for 65, this gets into indicators. Now, with indicators, watch the video. There's this nice, pretty, colorful chart that's in your textbook. Oh, it's on page... So I flip through right now here. It's on page 749. Okay, so if you're watching this, you need to turn to page 749, and hopefully you've already watched the video on indicators so you know what that means, okay? But just as a reminder here, okay, for 65, this one's a little out there. It's kind of the extreme indicator question. That's why it was a together one. You put 2 drops of this indicator that's just this generic, okay, H. Here's the short version here. H is the hydrogen ion. IN stands for indicator. I don't want to tell you how long it took me to figure that out. But anyway, that's where that comes from. And just this Ka value has of 1.0 times 10 to the negative 9th. Okay, so they also told us our Ka value, where the form where it's HIN, okay, where the weak acid is supposedly still together. This is our yellow version over here, okay, and then when it converts to this is going to be our blue version. Okay, so here are some of the questions it asks. The first off, it says, what color, we're going to titrate it with 100 mils of 0.10 molar hydrochloric acid. Now, in order to figure out how I'm supposed to know what color it is, come back up here for just a second and let's think about the Chatelier's principle. If I add in hydrochloric acid, I'm adding in hydrogen ion, and I'm going to force it to go back to the left. Okay, so as soon as it goes back to the left, we're reforming the original acid, so it's going to be yellow. Okay, so this one is going to be yellow. Now, for letter B, it says a solution is titrated with 0.10 molar sodium hydroxide. Okay, at what pH will the color change? Now, this is a reach. I'm just showing you this as like the extreme version. There isn't a question like this on the test. It's just showing you how potentially we could figure some of these out. Okay, so at what pH will the color actually change, where we're going to be going from the yellow to the blue? Now, here's what you need to know, and I know I've explained it somewhere, but the color change will occur, that's what this is saying right here. The color changes when the concentration, okay, our concentration of our new thing, okay, is essentially about 1/10 of what we're coming from, or vice versa. It's about 10 times, the dominant form, which is up here, is the when it's all still together, when this is about 10 times as strong as the smaller one. So how would I do that math? Well, let me show you how I would do that math. Again, this is a reach, just kind of the far reaches of this. If I know that my concentration, and this is a ratio thing, so that's why I keep coming back to this just a little bit. Alright, the way I think of it, is I only need about 1/10 of it to change in order for that to start to show up. Okay, now I know my Ka value, because they gave it to me, 1.0 times 10 to the negative 9th, okay, has to be equal to essentially 1/10 of the hydrogen ion concentration, okay, because that's, if I flip this around, here's my hydrogen ion, I can use pH, this is a reach, okay, so what I can figure out is that my hydrogen ion concentration, okay, if I set this equal to this, is going to end up being 1 times 10 to the negative 8th. So that means that at that time, my pH is going to be equal to 8.0. Okay? So 8.0 is when the color will change. And that's the math that justifies it. It's a reach, so don't, spend too much time worrying about it. The big thing is, can you understand, particularly in part A, where if I add more of this, it's going to force it to shift back and will make it yellow, and vice versa. Okay? All right, I'm going to do one more here. I'm going to go ahead and do number 72. So go ahead and look at 72. And remember, for 72, what you need to look back at is that chart that has all the colors on page 749. Okay, because and this is not something you have to memorize. One of the multiple choice questions we're going to do together is going to show you how this might be phrased, so you'll get a better feel for this. But on page 749, you've got all the color ones, and what it's looking at is, for all of these, it's a pH that's equal to 7.00, so it's flat out neutral. What would be the color of the solution if each of the following indicators were added? And you just need to find all of these indicators and figure out what color they would be. So our thymol blue is going to be a yellow color. Our bromethymol blue is going to be green, because you have both the yellow and the blue versions are present. So, good old color wheel stuff, that's going to form green. And then our methyl red is going to be yellow. And last but not least, crystal violet would be blue. Okay, and again, that all refers back to that chart on page 749. Okay, so there are a few more of the together problems, and I will come back with 93 and 95, which have to deal with the last portion, which is KSP, and that way we can kind of keep them all separate. Okay?